Let's talk about the chain rule, which is the most important of the rules for taking derivatives. Unfortunately, there's a lot of misconception that has been spread by a lot of the books about the chain rule and as how you use it. So I want to focus on how we really use it and how you're going to use it when you end up doing mathematical things in whatever it is that you're doing. So the chain rule tells how to take the derivative of a composition of functions. So I mentioned this briefly with the bug on the hot wire and the position changes, and that changes the temperature, so the temperature is a function of time, and so that's a composition. The usual way this kind of stuff is written is it's a real stretch of the notation that we use for functions, and so it really takes some thought. It's a very compact notation. So here's a kind of typical situation. And you have to kind of read this like a lot of functions. The function is what it does. And so, hey, let me get this out of the way. Function is what it does. And what happens is, so you take x, g does something to x, and that gives you some number. And then f does something to that number. And so this is something that happens quite a bit. A lot of times it's really subtle as to whether you're looking at a composition. So for example, if you look at the function I'm writing down here, let's practice reading this correctly. It's e to a power, and the power is 2x. That's a pretty simple function. But it's a composition because what happens is you take x, and then you double it, that's a function, and then you raise e to that power, that's another function. So x becomes 2x, which becomes e to the 2x, and so that's a composition. So what the chain rule says, and this is again a very careful use of notation, is we want to take the derivative of a composition. So I'm just going to start. We don't do math from left to right. We do it inside out or outside in or socks and shoes or something like that. And then we're going to have some function g. And so instead of doing f directly to something, we're going to do something else to usually the variable is x first. So let's get that in there. And so I've color-coded the parentheses so you can see really what's going on. You've got x, and then you've got that you've done g to that, and now that's some number, and then f does what it does to whatever's in the parentheses here. That's the cut and paste part. So then f of g of x. So for this example, the f function is the exponential function, and the g function is the doubling function. Okay. The chain rule is, well, it depends on how you want to look at it. It's complicated and it's simple. And the simplest way to look at it is to say, you know what? The derivative of a composition, this is one of the most important things that has been discovered ever in mathematics. The derivative of a composition is the composition of, I'm sorry, yeah, right. That would be a really big discovery. The derivative of a composition is the product of the derivatives involved, the product of the derivatives involved. And I mentioned this before, 2 scoops of raisins per package, that's a rate. 12 packages per carton, that's another rate. 2 times 12 scoops per carton. And so that's the chain rule right there. I mean, you can do all kinds of fancy stuff with limits, but the real bottom line is that you take the function g, some people call that the inside function, and then f, some people call that the outside function. And so there's your composition in its very abstract terms. And the derivative is, oh, wait a second. The derivative is the product, but where are you going to evaluate these functions? That's a fancy way of saying, what are you going to plug into f prime, and what are you going to plug into g prime? And it actually is often taken to be quite difficult and obscure, but it's actually quite simple. You plug into g prime what you plugged into g. So g had x plugged into it, so g prime has x plugged into it. It's another cut and paste thing. So, there's the deal with that one. The other part is what are you going to plug into F prime? And the answer is you plug in the same thing as you plugged into F. You're talking about doing something at that one point. So here, F had g of x plugged into it, so F prime has g of x plugged into it. I'm going to simplify the colors a little bit, but that's the deal. So if you're into this left to right thing, the chain rule says F prime of g of x times g prime of x. But, we've got to learn to deal with functions in a reasonable order as far as what they do. And the most important thing here is that this is a product. And so the derivative of a composition is the product of the two things evaluated or plugged in at the same place as they were plugged in before. Great. So some people seem to think that the purpose of doing this is to take, here's an example. I'm going to take the square root of 1 minus x times e to the x. This is a pretty typical chain rule exercise in a calculus book. You know what? Don't talk to people like this. They are just, pardon the pun, yanking your chain. This has nothing to do with how people use the chain rule in actually applying calculus to other things. So I'm not going to do that. That's not really much of a problem worth doing. So I'm not going to do it. Let me tell you something that I am going to do, and something that you're going to do, and something that is very important as far as actually using the chain rule in some kind of application, and that is given by the fancy name of implicit derivatives. And let me draw you a picture that's going to tell you what's going on here. I'm going to take the equation, not the function, the equation, x squared plus y squared equals 1. Now that's an equation for the unit circle. So I have drawn a very convenient circle. There's the equation, there's the unit circle. And the important thing to notice here is you look at a circle, and if you look at some piece of the circle, as long as you don't go where it's vertical, this red piece is the graph of some function. What function? Who cares? It's implicitly defined. You don't need to solve for this function. You don't need a formula for this function. You know what we're going to do? We're just going to call this function y. It's the y coordinate, so why not call it y? So we're going to call that that thing y. Okay, so now we're going to find the derivative of that function. Even though we don't know that function, we're going to find the derivative, but there's going to be a trick to it, and I'll show you straight away what the trick is, because even though we don't get to it, derivative is the slope of the tangent line. The derivative is the slope of the tangent line. So you can draw a picture of a line whose slope is the derivative. So if you just need the derivative at one point, you just draw that tangent line. That's pretty cool. So what I've done here is I've taken 2 points that have the same x coordinate, and one of them, it looks like the slope of the tangent, maybe that's -1. And this one here that looks like the slope of the tangent is, well, different. It's 1. And so what you're going to see here is that the bottom part of the circle is a different implicit function than the top part of the circle. It doesn't matter. You don't want to solve for it. You don't have to solve for it. It's a mistake to solve for it. But here's what we're going to do. We're going to use the chain rule, and what we have is this. We've got that x squared plus y squared is equal to 1. And I want to take the derivative of both sides. So here I am taking the derivative. I know this is super exciting. Well, I've taken the equation for the circle, taken the derivative of both sides. Now on the right, 1 is a constant function, so that derivative is 0. Fine. On the left, using the basic rules about taking derivatives, the derivative of x squared is 2x. The derivative of y squared is, just wait a second here. The derivative of x squared is 2x, but the derivative of y squared, That's a composition. We said y was a function. It's defined implicitly, but it's still a function. So the y squared here is a composition. Sorry, my dog just came in. Hi, Sammy. Y squared is a composition, so we have to use the chain rule. This is the way the people use the chain rule. This is the way the people use the chain rule. This kind of stuff is, those people aren't nice. Don't deal with them. Sammy, please. Okay, so what we're going to do is take the derivative of the composition y, that's a function squared. The derivative of squaring is doubling, so we're going to get 2y times y prime. That's what the chain rule says to do. You multiply by the derivative of the inside function. You get a composition y, then squaring, and the derivative is the product of those two derivatives. So the derivative of squaring is 2 whatever, and the derivative of y is, shoot, I don't know. It's 2y. I'm sorry, it's y prime. Okay, but now we can solve for y prime. And I'm going to skip some of the algebra, but what you get is that y prime is the negative of a fraction. Remember, we're trying to read things correctly. It's going to be the negative of a fraction. The top of the fraction is x, and the bottom of the fraction is y. What? The bottom of the fraction is y. What happens when y is 0? Well, when y is 0, you're at this point right here. Oh, I'm sorry, I'm doing it where you can't see it. And the tangent line has an infinite slope, so that makes sense. Anyway, let's look at a couple of others. At the point 1, 0, that's a point on the circle. X is 1, y is 0. Then, that's where it was vertical. Yeah, I better write that down. At the point 0, 1, that's the top here. The tangent's horizontal. So, but if you look, minus x over y is minus 0 over 1, which is 0. Yep, horizontal tangent, slope 0. At the point 1 over square root of 2, 1 over square root of 2, the square roots are there, so this thing, because you square both of the coordinates and add them, and you need to add up to 1, so you get 1 over square root of 2. The derivative is minus a fraction, and its top is 1 over square root of 2, bottom is 1 over square root of 2. Oh man, those are complicated. No, they're the same, they cancel. So the slope is minus 1. And so that's what you're seeing up at this part of the circle, that the slope is minus 1. That would be at the 45-degree angle. If you look at the other point with that angle, 1 over square root of 2, comma, minus 1 over square root of 2, that's a point on the circle. You square those individually, add them up, you get 1. And now you find that the negative of the fraction that we got specified, so bottom is 1 over square root of 2, I'm sorry, bottom is minus 1 over square root of 2, top is 1 over square root of 2, and that slope is 1. And so that's here, right here, where you've seen that at that point on the circle, the slope of the tangent is 1. So you can use the chain rule. This is the way people use the chain rule. This other algebra stuff is it's just there to make you feel bad, so don't do it. You're going to have to do some because people make us. But the way you're really going to use the chain rule is to do implicit derivatives. This is in my book, and it's kind of underplayed in all the other books, so you might want to look at mine first. Anyway, this has been a long video, and thanks for your attention. Don't let anyone yank your chain.